One of the key purposes of trigonometry is to solve triangles for missing sides, missing angles, and so forth. So today what we're going to be looking at is how we can be given information about a triangle. What information can we be given? And once we have that information, how can we use the trigonometric functions to find what we need? Before ever solving a triangle, we need to come up with some sort of convention to label our diagram. Now, every time we solve a triangle, every time we solve an application problem, it's really important to make sure that you have a good diagram. So we're going to start off by looking at this and saying that we have a right angle. Now later on, we'll be able to solve what we call oblique triangles, which are non-right triangles, but everything that we deal with the trigonometric functions is all based off of a right triangle. So one of the pieces of information we definitely have to be given is the right angle. Secondly, we also need to be given at least one angle and at least one side. So I'd like to demonstrate why that's the case. If we were given all three angles, let's just say that we were given that this is 62 degrees and this angle down here is 28 degrees, then we still have no idea what size the lengths of the sides are, because it could virtually be any size. So let's say that we were now at least given that this was 4 feet long. Now I should be able to find out what the other information is simply by using trigonometry and by using complementary angles. But let's just say that we weren't given any angles other than the right angle. We were told that that's 4 feet and this is 3 feet. Well, we could use the Pythagorean theorem in order to find out the hypotenuse of this triangle, but we still wouldn't necessarily know what the angles are until we do a little bit of work here. But we are given this right angle, and now we should be able to find some other information. So the convention we're going to use in order to come up with this is that the right angle is always going to be labeled as side C, capital C. And our angles are always going to be designated as capital letters, so capital A, capital B, and capital C. But now we end up looking over here, and the side opposite angle C is going to be labeled as a lowercase c. The side opposite angle B is going to be indicated as a lowercase b, and the side opposite A is going to be lowercase a. And this is in general going to be the convention we use in order to label our diagrams. So in this example, we see that we're given an angle and we're given a side. So technically, we only have two pieces of information that are given in this problem, but keep in mind that this is a right triangle. So the fact that it's a right triangle also implies that angle C is 90 degrees. So every time we solve a problem like this, we always want to have a diagram. So we want to draw a right triangle. Now it doesn't need to be to scale, we just need to make sure that it's a right triangle. And it's always important to indicate that it is a right angle as well by putting the little box inside. So if this is angle C, then that means that the opposite side is lowercase c. So we already know that this is 12.7 inches. Now, if we're going to label this side or angle A, it doesn't really matter which one we label angle A. So let's just label angle A down here and angle B up here. And as I said, it doesn't have to be to scale, but we're just going to assume that this angle of angle A is 34 degrees and 30 minutes. So in order to solve a triangle, that means that we're going to have to figure out what is side A, what is side B, and what is angle B. So we're going to have to find those three pieces of information in order to solve this triangle. So one way you could do, one thing you could do first is find angle B. You got to realize that angle A and angle B both have to add up to 90 degrees, since this angle C is already 90 degrees, and every triangle adds up to 180 degrees. So let's just go ahead and realize that angle B is going to be 90 degrees minus the other angle of 34 degrees in 30 minutes. Now keep in mind how to do something like this. We can convert 90 degrees into 89 degrees and 60 minutes. And the purpose of that is so that we could subtract 34 degrees and 30 minutes. And therefore we've got angle B. So angle B is now 55 degrees and 30 minutes. So I like to go back and label that inside of my triangle so that we can keep track. So we've got 55 degrees and 30 minutes. But now notice that we're going to have to find the missing sides here, and I'm only given the hypotenuse of this triangle. And so keep in mind that this is the purpose of trigonometry. This is the purpose of the trigonometric functions. I can simply say that sine of an angle, let's use the angle that's given, even though the angle B is still exact because I just subtracted it from the other angle. Sometimes the quantities that we find are going to be approximations from our calculator. So we want to do our best to use the original information that was given just to try to maintain as much accuracy as possible. Okay. So if we take sine of 34 degrees, keep in mind that that is opposite over hypotenuse. That's opposite over hypotenuse. But notice that that implies that this is the opposite side, which is A, over the hypotenuse of 12.7. And now notice that we only have one unknown, A. So we could simply cross multiply here to solve for A. We could find out that 27 or 12.7, sorry, 12.7 times sine of 34 degrees and 30 minutes is equal to side A. So trigonometry, the trigonometric function, helps me to find side lengths if we know an angle. And so in this particular case, when we did so, this just becomes on our calculator. We could even do it in another step as well. But notice that 30 minutes is 30 out of 60, so that's 0.5. So why don't we go back to our calculator? We make sure that we're in degree mode. And we're going to find 34.5 degrees. And we're going to take sine of that. So we end up getting this decimal here. Now when we multiply that by 12.7, that's going to tell me that this side is 7.19 inches. Now I want to demonstrate this one more time just to give you a perspective of what this means. Remember that the trigonometric functions are saying if I have an angle of 34.5 degrees and I take sine of that angle, then that means that the opposite side is going to be 56% of whatever the hypotenuse is. 56%, you could think about this as a percentage. So when I now multiply that percentage times 12.7, I now find out that the length is going to be approximately 7.19 inches. So A is 7.19. Okay, so I like to go over here and fill in 7.19. Now, anytime you have two sides of a right triangle, you can always find a third side by using the Pythagorean theorem. So that's one way we could do it. But we're going to go ahead and practice a little bit of trigonometry here just to recognize another way we could do this as well. And realize that since here was the angle given, 34 degrees, B is the other side that I need. It's adjacent. It's the adjacent side. So I could use either tangent of 34 degrees, 30 minutes, because that would be the opposite over the adjacent. Or I could use cosine, which would be adjacent over hypotenuse. So why don't we say that cosine of 34 degrees, 30 minutes is equal to the adjacent side over the hypotenuse. Adjacent over the hypotenuse. And if the hypotenuse is still 12.7, then notice that it's just solving for the other side that we didn't solve for using sine, which is b over 12.7. So likewise, if we were to cross multiply here and we get 12.7, let's see here, we get 12.7 times cosine of 34 degrees, 30 minutes, then that should give me the value of b. So let's go back to our calculator. So now if we have 34.5 degrees, because remember 0.5 degrees is 30 minutes, and we find cosine of that, now we're saying that the adjacent side is 82% of whatever the hypotenuse is. It makes sense that it's shorter, right? Because the hypotenuse is always the longest side. But now we're saying that it's 82% of 12.7. So when we multiply by 12.7, we get a value of 10.4, 10.5 or so, okay? Now in terms of the number of digits to use, okay, we've got b equals 10.5. In terms of the number of digits, we refer to this as significant digits. So when you take a look at this measurement right here, this has 3 significant digits, okay? But I don't want to actually put this one to, 10.466 and put 5 significant digits, because I can only be as accurate as the least accurate measurement. And so since this only has 3 significant digits, then 10.5 is sufficient for this value. And so now we've got all of our information. We've solved the triangle. Now, as I mentioned before, we could have, if we chose to, use the Pythagorean theorem using these 2 sides that we already had in order to find side B. There's lots of ways to go about doing a process like this. On the last triangle, we were given 1 side and 1 angle. So let's take a look now at this situation where we have 2 sides. So let's say we still have this right triangle. Okay. We put in our little box to show that it's a right angle. And now let's show that if C is 53.58, keep in mind that the hypotenuse is always C, 53.58 centimeters. And now side A, we're just going to have to pick as any of the other sides. So maybe we pick this one to be 29.43 centimeters. But once we do that, it's important to label all of our other information. So this is obviously angle C. If this is side A, then its opposite side is going to be angle A, or its opposite angle rather, which means that the only other angle is angle B, which also means that the opposite side here is lowercase b. So since we already know that angle C is the right angle, then these 3 pieces of information are what we need in order to solve. So a couple of things to do here. We could first of all just find side B by using the Pythagorean theorem. So let's start with that. So we get 29.43 squared plus b squared is equal to 53.58 squared. Okay, and now we can find the rest of this information here. After squaring each of those values, we can solve for b squared by just subtracting 866 from both sides, which gives me 2004.6915. Now I'm going out to quite a few decimal places here because I don't want to round too early. I want the rounding to happen at the very end of the problem here. So now we can take the square root of both sides in order to solve for b. And although we typically get plus or minus when we square root both sides, we know that the side length must be positive. So we can see that b is going to be 44.77 centimeters. Notice that I'm using the same number of significant digits as was given in my original problem. So that means that B is now 44.77. But now you might notice that we've got an issue because we don't have any angles other than the right angle. So we still want to be able to use trigonometry in some way. So let's just go ahead and say we want to find angle A. Okay. Now, although we could use at this point, since we've already done the Pythagorean theorem, we could use any sides we want. We typically want to use the sides that were originally given, okay? Because these are the exact values that were given in the problem. So if we're given the opposite side and we're given the hypotenuse, then the trigonometric function that deals with that is sine. Now notice I could use cosecant, right? Cosecant is hypotenuse over opposite. But if you take a look at your calculator, no calculator ever has cosecant, secant, or cotangent. So that's why we always deal with the three most basic trig functions, and sometimes the reciprocals come into play in other problems. So let's go ahead and use sine. So we know that sine of angle A is equal to the opposite side of 29.43 divided by the hypotenuse of 53.58. Okay. Now that's going to give me that sine of angle A, when I make that computation on my calculator, that should give me 0.549. But I'm going to keep going here because the more decimals the more decimal digits you use, the lesser the better the approximation is going to be. So now we know that the sine of some angle is 0.549. But notice that we want to be able to solve for angle A. So the way that we typically do this is by taking sine inverse of both sides. Taking sine inverse, think about the way that inverse functions worked in algebra. When I take f inverse of f of x, all I'm left with is x. So if I take sine inverse of sine of A, all that's left is A. So now we can take sine inverse of this ratio. And so if I typically take sine of an angle, I take sine inverse of ratios. And so now this button on my calculator will allow me to find out the angle if I'm given a ratio. So let's go ahead and punch in 0.549272165. 165. And now we go over to our sine inverse button, and hitting sine inverse gives me my angle. So it's approximately 33.317 degrees. 33.317, but we're going to go to 32 degrees because, again, the number of significant digits in our original problem. So this means that this is 33.32 degrees. And although we could use trigonometry again to find the other angle, the easiest way to do this is just to recognize that A and B have to add up to 90 degrees. So that means that angle B is simply 90 degrees minus 33.32 degrees. So angle B would equal 0.68 degrees. And there you go. So again, we've solved the triangle. So there may have been another way to do this. For instance, I could have used tangent in order to, I could have used tangent of A is the opposite over the adjacent, or I could have I could have used cosine in order to find angle B. There's a few different ways to solve any particular triangle, but the things that you have at your disposal are the Pythagorean theorem, any trigonometric function, and recognizing that once you have one angle, then the other angle is the complement of that. Now that we've seen a couple of examples of how to solve triangles being given certain information, we can solve all kinds of interesting application problems relating to triangles. And there's a lot more than you think there would be. So before we do this, there's one particular type of situation that occurs in a lot of applications, and it'll talk about an angle of elevation or an angle of depression. And so the best way to think about an angle of elevation is to look at just think of it in terms of your eyesight. In order to look at an angle of elevation, you're going to start with the horizontal. You're going to look straight out in front of you. And then you're going to tilt your head up, and whatever the angle of elevation is between the horizontal and whatever you're looking at, that is considered the angle of elevation. So this would be considered an angle of elevation. We'll call that theta. So it's always based on the horizontal. Now the angle of depression would be, again, from a horizontal and looking downwards. So instead of looking upwards to get an angle of elevation, you're now going to start at your horizontal and start looking downwards. So the angle of depression is the angle between the horizontal and the angle that you're turning to, or the line of, or what the line of sight is to where you're turning. And this is really important because I'm going to do an example involving angle of depression, and I want to show you that there is a particular situation that a lot of people misrepresent the angle of depression as. So both of these are always starting from the horizontal. Okay, so let's do an example. As I mentioned, with any problem in trigonometry, it's always important to draw a triangular diagram, especially when it comes to application problems. When you have an application problem, it's also really important to be able to visualize what's happening. It may take you a couple of times to read through it, but this one says from the top of a 210-foot cliff. So the first thing I'm going to realize is that I'm standing on top of this cliff. Okay, and here's a cliff. And David observes a lighthouse that is 430 feet offshore. Okay, so that means that here's the shore, or I'm sorry, here's the ocean. And there's a lighthouse that's going to be out here somewhere. Okay. Now you don't have to draw this particular picture in order to be able to understand what's going on, but you should recognize that if you're standing somewhere on top of this cliff, and you're looking down at this lighthouse, it says find the angle of depression from the top of the cliff to the base of the lighthouse. All right, so that must mean that we need to draw that line from David down to the base of the lighthouse. So based on this situation, we're trying to find the angle of depression. Now keep in mind, the angle of depression is from the horizontal. What a lot of people would do is say, well, this is the angle going down to the lighthouse, so that's the angle I'm trying to find. When in fact, that's not the angle. The angle of depression is always based off of this imaginary horizontal and turning downwards. So this is the angle that we're trying to find. Let's call it theta. It tells us also that this is a 210-foot cliff. It also tells us that offshore, the lighthouse is 430 feet. So notice that even though this is kind of this little sketch of this scenario, this is still implied to be a right triangle because the cliff meets the water at a right angle. Now the issue that we're running into here is simply that this angle up here is outside of the triangle. So we can't really use trigonometry to find that unless we have another triangle. So we've got two options. One option is extend this triangle all the way over until you get to here. Extend it all the way down. Okay. Or recognize based off of our angle relationships that this line is parallel to the water. And therefore this angle by alternate interior angles is also the same angle as theta. So from David looking down to the lighthouse, this is our angle of depression. From the lighthouse looking up to David, this is our angle of elevation. Turns out that both of these are going to be exactly equal. So now that we're given this angle, or that we're trying to find this angle, we're given the opposite side and we're given the adjacent side. So we've got to realize that the ratio that deals with opposite and adjacent is tangent. So tangent of theta is equal to 210 feet divided by 430 feet. Just keep in mind the reason for that was because the opposite side is 210 and the adjacent side is 430. All right, well, if we want to find theta, then theta is simply tangent inverse of whatever the ratio 210 divided by 430 is. Okay, so let's practice go into our calculator. So we would say, what's 210 divided by 430? So there's the ratio. So the ratio between the opposite side and the adjacent side is 0.488. So if I take tangent inverse gives me 26.03 or so. So theta is 26.03 degrees. But notice that we only have 3 significant digits. And so it's actually, in fact, 2 significant digits, because this being the fact that the trailing 0, the only significant digits are the 2 and the 1, mainly because this could have been rounded to approximately 210 feet, approximately 430 feet. So we're actually going to write this as 2 significant digits, or theta is 26 degrees. So just keep in mind that when you're dealing with application problems, to always draw the diagram and fill in the things that you know. But in addition to that, when you're dealing with angles of depression and angles of elevation, it's always based off of the horizontal looking upwards or the horizontal looking downwards.